Welcome, everyone, and thank you for joining us today. My name is Paul Donahue, and I will be your host. We ask that you please keep your device muted during the session, and if you have questions, please direct them to me via the chat function. We'll do our best to answer these questions at the end and to follow up with any unanswered questions by email. These Tech Talks have been designed to provide straightforward insights into radio frequency components. We talk about the related technologies and the extra design and engineering value that is added by a custom manufacturer such as Quantic TRM. To begin today's session, I'm once again pleased to introduce Quantic TRM's Chief Technology Officer, Shaun Moore. The author of 2 U.S. patents and numerous white papers and technical articles on passive microwave technology, Shaun has been with Quantic TRM since the late 90s. And over the years, his passion for the job and for solving problems has only increased, especially when it comes to resolving our customers' design and engineering challenges. So welcome, Shaun. Can you share an overview of today's topic and your objectives for the session?
Yeah, absolutely. Thank you, Paul. So what we're going to talk about today really is power combining and the different types of power combining that are available to us. The 2 most notable ones are coherent power combining and non-coherent power combining. And we'll talk about really what the differences are between those 2. And then all power combining is not 100% efficient. And we'll talk about, what makes it efficient and, how is a combining efficient and why it's efficient. And then when it's not efficient, where does that energy go for both isolated combining and non-isolated combining? We'll wrap it up with a summary and talk about some Quantic TRM differentiators.
Well, that sounds good. So maybe to get started, what's the best definition of power combining?
Sure. So as we look at what power combining really is we are instantaneously combining energy from multiple sources. And a thing to remember here is that when you're dealing with RF energy, everything's a vector. Therefore, it has a magnitude and a phase. The phase component of that vector can mean that the energy will either combined together or coherently, or it will be out of phase, in which case some of the energy will be subtracted and some of it will be added. So in a little more layman's terms about that is if we're combining two signals, they're broken down into vectors. The energy that is constructively summed is delivered to the output, and the energy that ends up being subtracted because of a phase differential is not delivered to the output. And that energy has to go somewhere since we have a thing called the law of conservation of energy. In an isolated combiner, that energy is directed over to the internal terminations in the power combiner and are then converted over to heat. In a non-isolated combiner, that energy is reflected back towards the sources, which will create a higher VSWR condition for those sources, in which case then those sources will have to absorb the energy.
Okay, well, that makes sense. Now, it says here that we have isolated and non-isolated combiners. What exactly determines which type to use?
Sure. Now, there are a few different types of scenarios as far as what your application is that really kind of dictate really the type of combiner that you should be looking at. And there are multiple advantages for each type of combiner as we're going through there. So the big question is, why do you want to combine signals? If you want to put multiple signals on a common path, and these sorts of applications are things like taking multiple radios and putting them on a single antenna. Sometimes if you have different sources, whether it be spread spectrum type sources or any other sorts of things where you're taking different signals and putting them onto a single path. For that sort of scenario, an isolated combiner is probably the best solution. Kind of the downside, if you will, of having these sorts of signals coming in using an isolated combiner is that each signal will see 3 dB worth of loss, or half the power will be dissipated within the power combining circuit just to get that energy lost and due to the mismatch energy. The lost, and the good news here is that the lost energy will not affect the VSWR of either of your sources, and that it can be a very good way of combining multiple sources onto a single line. 90-degree hybrids are specifically good at using this sort of application, since you're coming from different sources anyway, that usually phase does not matter. If you're trying to do a power combining where you're trying to increase power by putting things in parallel, things like amplifiers in parallel to increase the total power that you have a common source, you want to divide it, then you want to recombine it again. Then you have to start asking questions: how well are the amplifiers matched? And can the amplifiers handle a little bit higher VSWR? In both of those cases, you can use either an isolated or a non-isolated combiner. And really the choices there of which one you decide to use really depends on the questions that we just asked earlier: how well the amplifiers matched, and can the amplifiers take a little bit of a higher VSWR? If the answer is that they're not matched very well and they can't tolerate much VSWR, well, maybe you're back at an isolated power combiner. However, if you can have well-matched amplifiers and the amplifiers can tolerate a little bit of increased VSWR, very often a non-isolated solution, first of all, can be more cost-effective, but also can also be very more efficient in the long run because of the way we typically build those non-isolated combiners.
Can you maybe give us some insight then into how power combiners are typically used?
Sure. Now, sort of expanding on this sort of idea over here, some graphics on the screen here should help explain really what I mean by coherent combining and non-coherent combining. Coherent combining means that you take a common source, you typically divide it in an equal phase manner. You then have two or more sources to increase the total power, and then you recombine it in the combiner. So in the example here, we have a source, we have two 10-watt amplifiers, and then we're recombining it. In the coherent example here, what we have is we have one signal coming in, being divided out, amplified, and then recombined. So we're taking the signal, multiplying it by two 10-watt amplifiers, combining it coherently, ending up at 20 watts total. In the non-coherent case, where we have two separate sources using the same two amplifiers, we now take those two individual sources, increase both of them up to 20 watts, and then put them through a power combiner. We end up with 5 watt with two different signals as opposed to one signal, but now we have two signals at 5 watts each. Now the power combiner has to take that total of 10 watts worth of power that we're losing, 5 watts from each source, and has to dissipate that in heat. So that is the difference really between coherent and non-coherent combining. If we are using the non-coherent case with a non-isolated power combiner, then that 10 watts would then be, or half the power would then be reflected back towards those sources. And we'll go through a little more detail with that in a few minutes.
Okay. And maybe could you add a little more context to what this screen is telling us?
Sure. So for isolated combining, the thing to really look about here is that we really need to go in there and really decide really what it is that we're trying to accomplish. And like I said, with this sort of scenario, there's actually quite a few different ways we can use this divider and combiner combination to accomplish this, where we have a signal source coming in, we divide the signal up, run it through a series of amplifiers, and then recombine it to end up with a much higher power than any one of the amplifiers on their own could deliver. Sorts of things that we like to look at here are things that have good external terminations to handle if there are any reflected energy coming back from the combiner due to phase or amplitude mismatches, ways that can absorb that heat. Things that do that quite well are actually a traditional 0-90 hybrid, a ring hybrid, or a Geisel combiner. These things all have 50 ohm terminations on the isolated port, which makes them really well suited for building this sort of isolated combiner. This way, if there are any differentials in those amplifiers, they can then go ahead, and any of the differential energy can then be absorbed by the resistor isolation network. The other thing also that we can look at there is that if we were to use a 90-degree hybrid as opposed to an in-phase network as both the divider and the combiner, that also works out to be very efficient because any error in the divider or combiner network is actually canceled because you're using the same device. So it becomes self-correcting, and that any of that energy does get ported off to that fourth 50 ohm termination of the device. The one thing I want to point out here, using the traditional in-phase networks, is a Wilkinson sort of power combiner. Because of the nature of the isolation resistors being in a balanced mode, typically does not have a good thermal path to ground, and therefore really typically can't handle that much power in the reverse mode. Once we start getting a little bit of phase errors. So that is one kind of caution against using a Wilkinson style power divider as a power combiner, because the way that the isolation circuits are configured in that particular device, really power handling is limited.
Okay, and how about for non-isolated combining then?
Sure. Now, for non-isolated combining, we establish basically the same sort of ideas as far as to how this works. Really, the only difference here is that for non-isolated combining, instead of that excess energy being ported off to the terminations of the combining network, it gets reflected back to the source. So what's key here in this sort of a network is that the amplifiers need to be matched very well. And by doing so, you can actually, if they're matched perfectly, then there will be no reflected energy coming back to the amplifiers. So in this case, it can be very, very efficient. The sorts of things that we do for a non-isolated combining are things like radial combiners, which typically are built for very high power, since they're very much airlines along with that sort of airline sort of construction. Therefore, the material losses in those combiners are very low, and therefore they can be very efficient if the amplifiers are matched quite well. Now, what you can do to see whether or not this is an opportunity for you is we can calculate how much energy is going to be reflected back to the amplifiers. This is as long as we know what sort of match we expect out of the amplifiers, we can then go ahead and calculate really how much energy they're going to see whether or not we can afford this, and then get the advantage of the more efficient, less loss in the combiner through a radial combiner.
So what can you tell us then about energy loss?
Sure. So energy loss, you kind of talk about this, but there's a time when you have to do a little bit of math. And in general, if you take a look at the graphic on the left there, what you'll see there is that if you take the phase error, what you get between two signals coming in, a sine square, a half angle sine squared function, as you see there, will show you the percent of power loss due to phase cancellation. And as you can see, if you can keep the phase down to below, say, 15, 20 degrees, the loss in energy due to phase errors is quite low. As you increase the error in phase, so goes up the percentage of power you're losing. A 90-degree phase error, you're going to lose half the power. And at a 180 phase error, obviously, it is all going to subtract, and you're not going to transmit any energy out whatsoever. The graphic on the right is another interesting one. It shows the same graph as what you have on the left, except that I've added the parameter there of amplitude imbalance. And as you can see there on that graph, with the green line and the blue line and the yellow line, those errors track very well to the perfect case, and really until you get up to the red line, which is a 3 dB error on amplitude, really before you start seeing any sort of significant movement on what the efficiency is. So this over here really shows how important the phase is to a combining network, and really how insensitive the amplitude error is between your amplifiers. So you don't necessarily need to have a perfectly matched amplifier from an amplitude standpoint. They can vary a little bit, and it really won't affect your overall combining efficiency. What is important though is phase. The black line on that graph on the right there shows the amount of loss that you get due to phase instability. And as you can see, if your phase is below 10 degrees, you're going to lose very, very little energy when we're building these power combining networks. So really, phase matching is very important for your amplifiers going through here. And if you can keep the phase down quite low, the reflected energy and the amount of heat dissipated in the combiner can be very manageable, and you can be very successful.
So where exactly does this lost energy go when non-isolated combining?
Okay, so the energy of what we just talked about there was regardless of whether it's an isolated or a non-isolated case. In the isolated case, that energy gets dissipated in the resistors in the matching network. Now, in a non-isolated case, that energy gets reflected back to the source. And many people have come to me and said, well, how do I know how much energy or how bad is that VSWR actually going to get with a various phase error? Well, this graphic here shows a way to calculate that. And we can calculate what the additional reflection is, and how does that affect your reflection coefficient. Now remember, the definition of VSWR is it is a power ratio of reflected energy over the incident energy. So if we think about the non-combined energy as being additionally reflected energy, it becomes a simple matter then of going back and determining what the impact it has to reflection coefficient, and then therefore you can recalculate the VSWR. So in the example that I have on the page here, the power combiner starts off with well-matched signals as being a 1.2 to 1 VSWR, which is sort of a typical spec of what you get with a power divider. And if we had a 20-degree phase error, which is not a horrible phase error, but it is creeping up there a little bit, you will see that your reflection coefficient will increase by 0.167. What this means then is if you add the 0.091 reflection coefficient of the 1.2 to 1 VSWR to the 0.167 of the additional energy reflected due to the 20-degree phase error, you'll end up with a total effective reflection coefficient of 0.258. So this will effectively raise the VSWR that the amplifiers are going to see from a 1.2 to 1 to a 1.7 to 1. As you can see, now once you get much above this, the 20-degree threshold, the VSWR becomes quite significant, and chances are the amplifiers won't be able to handle it. But if we can keep that phase error lower, then the effective VSWR due to phase mismatch becomes much more manageable. This is why we typically like to say we should keep these mismatches below, say, 15 degrees or 10 degrees in order to keep that much more manageable. I said on the graphic on the right hand of your screen, does help show that, as well as I have a table down there correlating the reflection coefficient back to VSWR, so you can quickly look up and kind of give you a rule of thumb as to about where you're going to land. As you can see, as your reflection coefficient hits 45 degrees and 50 degrees, the VSWR becomes just completely unmanageable. So really, in this scenario over here, we really need to have that match down below, say, 15 or 20 degrees, worst case.
Well, great information as usual, Shaun. Would you like to summarize?
Absolutely. So really what we're looking at here is, there's different ways of power combining, and there's different applications as to why you would want to do some power combining. You could take multiple signals from different sources and try to put them on a single line. This way we're sharing an antenna or other sorts of resources. And in that case, a coherent combining is really the best way to do it. Or are you trying to go in there and trying to increase your total power availability because your amplifiers just can't put out as much power by themselves. So therefore, you know, put some parallel and increase power. In those cases, we could be using either coherent or non-coherent sources. When you're looking at a coherent or non-coherent source for signal combining, the thing here really to keep in mind here is that the energy has to go somewhere if you don't have a good phase match, and that really depending on how much VSWR you can handle, that will really dictate as to whether or not we're going to go in there with a coherent or a non-coherent, or excuse me, an isolated or a non-isolated solution. I think it's really interesting to go through and very often as you look at what you have for matches of amplifiers, if you're thinking about just making sure your overall efficiency without wasting a lot of energy, if you can get your amplifiers matched pretty well, very often you can actually benefit from a non-isolated combining solution. And very often it can be the best you know, scenario for you going through there. It's always a good trade-off, and it's always good having the conversation to see really which method of power combining best suits your needs.
Well, that makes sense. And maybe could you share a little bit along the lines of the key Quantic TRM differentiators?
Sure, absolutely. And really what I think the key differentiator I think that I want to leave you with here is that we want to work with you to make sure that you get the best solution for your needs. And I think that is really what we do here at Quantic TRM and where we thrive at. We like to listen to our customers, find out really what it is they're doing, and from there we will tailor our response and the way that we're going to build the network specifically for your needs. Necessarily, I want to also point out that because we're going custom work, it doesn't necessarily mean that it's going to be costly. We try to leverage off of designs we've had in the past, so we're almost never starting with a blank piece of paper. Part of what we do also is, as part of evaluating those needs, is we have a careful selection of the materials and design approaches that we have to make sure that we can meet your needs. We also do an awful lot of custom packaging and designing for very difficult environments for both the terrestrial aircraft and space. So therefore, we always address all those mechanical needs as well as the electrical needs. And also, we like to do a lot of the testing to prove and give you the objective evidence that the part does meet all your requirements. And I think the bottom line here is let's think of Quantic TRM as a solution provider that can also give you some hardware.
Well, that sounds good. And we do have one question, and that is, when combining signals that are in different frequency bands, are there other methods that are more efficient than the isolated combining you described that has the -3 dB of loss?
Yeah, absolutely. And this is something I think where you have to keep in mind that if you're combining signals that will always be in two separate bands, very often your better solution actually is to build a diplexer and feed that backwards. They will not have the insertion loss hit, and therefore they will not have that 3 dB worth of loss going through there. By having a diplexer where you have a low pass or a high pass network or a band or two band pass networks, where you're always going to be in the same frequency range on each path, and they're very different frequency signals where they can be separated. The combining networks that we talked about today were really if we have signals that are either in overlapping frequency ranges or using the same frequency range. Therefore, in those scenarios, you're going to have to take either the 3 dB hit for the non-coherent signals, or have them be additive in the coherent case. But I think the thing here also is that if you are always going to be in separate bands, then you certainly can use a diplexer or a triplexer or other filter network to act as your combiner to put those different signals on a common line going out to an antenna, for example.
Okay, well, thank you, Shaun, and thanks again to everyone for joining us. In conclusion, I think the bullets on the screen here say it all. And if you are a customer and you have additional questions, we would love to hear from you. Please feel free to call our engineering hotline. The number is on your screen, 888-677-6877. There's no cost associated with these conversations. And if you are one of our field sales representatives, of course, your calls are always welcome, and you can connect with us through the portal. Going forward, the next Tech Talk will be on Tuesday, April 23rd, and the topic will be Hybrids 2.0. Thanks again, everyone. Thanks, Shaun.
Thank you.